So there's no air resistance to slow the object down. And I forgot to start recording when I started talking. So this is Q1 on the second page. It's the golfer problem. And we're just getting set up right now. So horizontal motion doesn't change. Vertical motion does, because what does it do as it falls? It's got an acceleration, so it's going to fall faster and faster until it hits the ground, and then it will have a force up, which will cause it to stop. So during the time it's in the air, when we do a projectile motion question, we really are only working with the time in the air, just barely after it was hit or launched, and just barely before it hits the ground. Because if I do before it was launched, I have to deal with that force. And if I do when it hits the ground, then I have to deal with that force, and I'd rather not. So we just keep everything in the air. So we consider projectile motion to be only when the object is in the air. All right, so now what about vertical velocity? Well, vertical velocity, I do not know. That's a question mark for me. So now I've filled out my velocities. Now, what about acceleration? What acceleration do we have? We have gravity, which would be it's a vertical acceleration. It pulls you straight down. Gravity doesn't pull you left and right. Gravity pulls you towards the center of the earth. And because we have no change in speed horizontally, we have no acceleration. So once again, because it's constant velocity, I don't have an acceleration. And time in the air is also a question mark, because of course that's the question they just asked me. Move this chat box down just a little bit. There we go. I'm going to wait right there. So out of that question that looked like they didn't tell us anything, look at all the stuff we actually knew. Yes, there are a lot of zeros, but we knew they were zeros, which instead of guessing that they're zero, we actually know that they are zero based on what was said in the question. So I'm going to leave that up for a minute, and I'm going to come back over here and read it. So the first question, how long after the ball leaves the club will it land on the fairway? How long after the ball? So what is our first question? First question is time in the air. So now I have to pick one piece of information or the other, one of those kinematic equations or the other, which I will write back over here. From way before. Ooh, not alpha. That's what Nathan's doing. And okay, giving people time to write and think. I have too much blood in my caffeine intake system again. So I'll have to remedy that. Some people need blood. I need caffeine. It's kind of a different thing. It's all good. All right. So time in the air. Let's see. Which equations do I not want to use? I don't want to do this one. Why not? I don't know enough information, and time is not in that one. It's going to be tough to solve for time if time is not part of the equation. Okay. So then I pick from the other two. I'm not going to pick this one. Why not? So I don't know the final velocity. I don't know final velocity, and I don't know time. Here I do, but acceleration I already know. Doesn't help me. So I'm going to do this cute little equation, except that I'm going to do it vertically. Whoops. I'm going to use the vertical one. Y final equals Y original plus V original t plus 1/2 a t squared. Once again, time in the air I need to solve for, and so I need to know all the other pieces. The vertical side is where I know all these other pieces. And the a doesn't cancel out the t. So here we go. Y final is I hit the ground from the top of the driving range. My initial velocity was 0. My time is unknown. My acceleration is due to gravity, and my time is still unknown. So I'm going to wait right there. All right. So that gives me 0 equals 4.9 minus 5t squared. So with my cool algebra skills, I'm going to solve for t, which means I'm going to move the 5t squared to the left-hand side so that I'm going to add it to both sides. Then I'm going to divide both sides by 5. What is that? There's my phone. It's really close to 1. 4.9 divided by 5. 4.9 divided by 5 is 0.98. And then my last step will be to take the square root of both sides. So t equals 0.99. All right, now I'm going to wait. You guys out there can unmute and ask questions, or you guys in here can ask questions. Yes, Ruben.
I use the velocity final square to find the final velocity, and then I use the other one. What you did is easier, but that's still
Yeah.
valid.
Okay, so you could still do this one. What Ruben asked was this. Can I use this one first to find final velocity? And then go up here and use this one to find your time? Yes. Yes, you can. You can do it as a two-step. Yep, you get the same answer within round off, depending on where you round off. So I'm going to wait there. So as usual in physics, one of the problems with physics is that there's lots of ways to work a problem, oftentimes. So that's good, but that means if Autumn asked Dom what he did, you might You might both be doing the right thing, but they look very different. And so then you confuse each other when you're trying to help, because he thinks of it like this and you thought of it like this, and you're both right. But when you try to check each other, since you worked it differently because of the way you see the problem, you end up with this is not helpful. I am completely lost now. I thought it was kind of okay, but now that, right? Or both of you are completely wrong and you don't know who's wronger, to use bad grammar. So if you're both doing it incorrectly, you will have different paths, and then it's hard to figure out what you should have done. So physics has that kind of, it depends on how you think of it. Which is why sometimes if you don't understand what I said, asking Nathan is a good idea, because he thinks about problems very differently than I do. Some problems we think alike, but most of the time we come at it from two completely different points of view. So that can be helpful, but that can also be confusing. It's just, he who does the work does the learning. So if I'm the only person in the room doing the work, I already know how to do this. But I do know how frustrating and aggravating and this can make you. So let's look at part B. What horizontal distance will the ball travel before striking the fairway? So now they're asking me to find, this value. How far away? What is our range? Part B asked me to find our range. So I'm going to go back and look at all the information I know. Range is a horizontal thing. So if it's a horizontal thing, we should probably use horizontal stuff. Okay. And what are we trying to find? We're trying to find this distance, right? This range. So that probably means I need to use the equation that has that in there. Bless you. So either I want to use this one or I want to use this one. The bottom one is not going to work. Why not? Because your acceleration is, if you put a 0 here, guess what happens to all this other part? It's all 0, so now we can't answer the question. And we get that our final velocity is equal to our original velocity. Yes. Yes, they are. Yes. 20 squared is equal to 20 squared. I think I told you about the day that Jess Patton, who's Joella Patton's one of her older brothers, worked for about 45 minutes in class and goes, Miss Wilson, can you check this? I think I got it. And he had proved that power was equal to power. He had a whole front page of algebra, about half of a second page, beautiful relationships, and he proved that power was power. Like, yeah, Jess, that doesn't answer the question. What did I do? You proved that power's, oh, I wasn't looking for power. I was looking for work. Yeah, it's okay. Sometimes you get going really good and you're so excited and you're pulling numbers in and you're going somewhere and it's like, well, crap. So this time I'm going to do x final equals x original plus v original t plus 1/2 a t squared. And I'm going to come back up here and see what I know. I know that the original position was 0. I know that the original velocity was 20. And now I know the time is 0.99. As I scroll the top, I also see, so now I know this piece is 0.99 seconds. I can fill that in. So now I know that my acceleration is also 0 because there's no air resistance. Hey, look at that. All I need to do is number crunch. This part is 0. So 20 times 1.99 is 1.98. Is that right? Yeah, that doesn't. 20, my bad. Yeah, 8.98. Okay. I don't know why I'm struggling this morning. 19.8. Yeah, it's the why am I not carrying? I don't know. All right, eraser. 19. Yeah, that was careless. 19.8. And it would be meters. And that seems reasonable because if it was in the air for about a second, it should go about 20 meters because 20 meters per second is the speed. Okay. Part 3. What is the acceleration of the ball half a second after being hit? I don't even have to do any math on this one. What is the acceleration of the ball? Due to gravity. At every second. At every moment in time, the acceleration is due to gravity because your free body diagram would be force due to gravity. And if you want to go back and look at your chart, you can see that it has no horizontal velocity, or no horizontal acceleration, it only has gravitational acceleration. So you could have gone back and looked at that too. Yes?
If it were to have horizontal acceleration,
we'd have to use the Pythagorean theorem.
Okay.
Yep. So if it has an acceleration across and an acceleration up and down, we have to use Pythagorean theorem to find the hypotenuse. Calculus people get to do that. You guys are in physics 1, so you don't have to do that.
Okay.
Nathan has to do that. But he has to do it with calculus. So, you know, you do what you do. It's always good when there's an easy one. There's an easy part. So, when anything is in the air, what's the acceleration due to? Gravity. Gravity has the same acceleration all the time until you get way out in space. And then it doesn't go away, it just gets smaller. So there is never a time when you don't have gravity. Even if you go way, way, way out in space, there's still going to be gravity. It'll just be little tiny gravities from all the other objects in space. So Jupiter does in fact have an attractive force on you. But you don't have to be worried about pulling off the Earth and getting sucked into Jupiter. Because it's wee tiny, even though Jupiter's ginormous. Like 100 million Earths ginormous. It's just, the numbers in space are too big to even think about. We're going to get through one problem today, aren't we? Yeah, all right. Okay. Letter D, calculate the speed of the ball 0.80 seconds after it leaves the club. Speed of the ball. Okay, speed of the ball. Okay. Well, part of this I know pretty easy. What is its horizontal speed? Always. In this problem, the horizontal speed is 20 meters per second. I'm going to need to do something to find its vertical speed. And so, Ruben, this is one of the places where, had you worked the problem the way you worked it for part A, you would already have the answer to part D. So it took you longer on A, but now you have the answer to D. So if I want to find the vertical speed of the ball, I'm going to use vertical things. And I'm going to do vertical speed is going to come from V final equals V original plus AT. I don't know vertical speed. I know we started at 0. I'm going to use vertical info. My acceleration is -10, and my time in the question is 0.80. Not squared, you doofus. So we're going 20 meters per second this way, and we're going -8 meters per second this way. So what is our overall speed? Be the square root of 20 squared plus -8 squared. Pythagorean theorem. The only equation that I know probably every kid in this school knows and can say. I have never had a kid, I don't care how weak you are. I've had kids that couldn't solve this. I've had kids in this room that can't solve that. Physics is tough for them. I've had kids that can't solve that, but I've never had a kid that didn't know how to do the Pythagorean theorem in all the years I've taught. Even my kids that when I had a SPED class, they could still do Pythagorean theorem. I don't know what we're doing, but you guys have that one. The math department has done a wonderful job on that formula. Some of you can sing me the quadratic formula, and some of you can't. But anyway, so since we have 2 parts to our motion, we have to have our 2 speeds, and we're going to have to combine them because it's a vector. So in this case, it would be the square root of 464, which is about, somebody got that? Oh, let's see, 484 is 22. 21.5, yay, thank you. Maybe we're down to the final part. Yay! With what speed will the ball strike the ground? Okay. Guess what we're going to do? We're going to do D again, but this time with the time of 0.99. So let me get over here. A nice clean sheet. So I'm going to do just like E is going to get work just like D. D. But time is right as it's hitting the ground. So V final equals V original plus A T Okay. So this equals -9.9. So now we're still going 20 meters across, but now we're going down at 9.9. All right, 400. 98.01. Is there 22.3? Okay. So this is our speed as we hit the ground. Our speed as we hit the ground. Yeah.
I mean, I guess it's kind of like an extreme question. How come the units work out? When you square it, do you square meters and?
Yes, yes. Units get treated just the same as everything else. So in this case, we'd have c squared equals 20 meters per second squared plus negative 9.9 meters per second squared. So then you get 498.01 meters squared per second squared. And then when you take the square root, so the units act like they were just x's and y's in the problem. But yes, that's a good question. Okay, so now you got to do these by yourself. No. One more thing, and then I'm gonna tell you which ones I want you to try before you come back tomorrow. So, why does this look like a parabola? Why do we get this particular motion? So when we do these problems, just for a second, let's do a really simple one. Let's say I launch a ball up at 30 meters per second. Okay. So if at time 1, time 2, time 3, 4, 5, and 6, what is its vertical? So let's make this easier on you. The vertical velocity is 30 meters per second. Horizontal velocity is 20 meters per second. We'll just kind of do what we did in the last problem. So at time 1, we start down here. Where would we be at time 1? What would our speeds be? Because here we're going 20, and we're also going up 30. So I'm going to move from here to here. What do I do at time 1? What are my speeds now?
20 horizontal, 20, 30.
Still 20 across, but gravity slowed me down by 10. That's what the acceleration means. It slowed me down. So instead of going, so now I'm going 20 this way, and I'm going 20 this way. So my path is now here. What about time equals 2? Oh yeah, I'm still going 20 to the right, but how much am I going up? 10, and then I'll be going 20 to the right and nothing up and down. And then I go 20 to the right, but 10 down. And then 20 to the right and 20 down. Do you see what's happening? If I mark where the ball is, it has all these different speeds, but if I mark where the ball is, it's here, then it's here, it's here, and it's here, here. And so we see that parabola, because the horizontal piece keeps doing what it's supposed to do. It does the same thing every time, but vertically you're changing the heights, and so that causes your ball to move up or to move down. And that's why we have to break it into 2 parts, because the 2 motions are different from each other. One is just a, hey, I'm going 55 miles an hour down the interstate. The other one is the interstate is going up and down hills. Okay? So that's the overall big picture of what's happening. So how can I make my projectile go farther? What are some ways to make the projectile go farther if I don't change the launch speed? I could have gravity be different. So on the moon, okay. So on the moon, if we did this same problem, what would be different on the moon? So the time would be much longer because gravity is a lot smaller. But if time is longer, what else changes? Like if I was to hit this same golf ball on the moon, now it's going to go a lot further forward because it's going to spend more time in the air. It's still going 20 meters per second the whole time. That's unaffected on the moon. The horizontal part's unaffected on the moon. But the vertical part will be slow going up and slow coming down. So I spend a lot more time in the air. If I spend a lot more time in the air, I'm going to horizontally get a lot more steps in. So playing on the moon would be really cool because we could all drive the golf ball, assuming you could hit it, which I've seen a lot of golfers not be able to do that. Assuming you hit the golf ball, it'd be more fun because you'd feel like a Tiger Woods or a Phil Mickelson or Justin Spieth. Anyway, dude drives like 300, so plus. But that gives you an idea. So I'm gonna stop the recording right here, and then I'm going to I'll post this in a little bit.